Yeah, so last part of this one. So I want to say about discrete models. Again, I'm going more and more into things I know less and less about. So I, yeah, so anyway, so next Shubhajit will talk about, I don't know exactly what he plans, but I think.
Yes. So now this is a great opportunity to put him on the line.
Please.
Shubhajit, when are you planning to
okay,
start?
so I, do you hear me? Yeah.
Go ahead.
Okay, so I was thinking, so that's why maybe having a 1 week more would be good. So I'm going to discuss a subset for some other reason. This Befara's paper has observed dimensions of SLE.
Okay.
I'm going to read that a bit more details anyway. So I was thinking about presenting that, but I would be probably a bit more comfortable because of the time issues to have 1 week in my hand. So maybe not next week, but next to next week, if that's okay. I mean, anybody can.
Yeah, absolutely. Yeah. So next week we have a well-deserved break. Good.
Yeah, so that will be good. Okay, so then it's more continuation of SLE, but I thought is there some plan at some point to go to these Gaussian free-field contours or stuff like that? I somehow had vague impression that was planned. I don't know why.
Shubhajit, weren't you planning to do the harmonic explorer, something like that?
Yeah. So okay, so but that again I have to read a bit. So probably I do that, but let's start with this one because anyways I'm going to read it. So I think it's better for me also. So
okay.
So you will see. Okay, no, that's good actually. So this leads. So firstly, there is a bit more of SLE doing this Hausdorff dimension estimates. I showed very few computations with SLE. I mean, I gave a basic idea of how some computations are done, but more will come in Shubhajit's lecture, and then also more discrete models. Here I will touch very, very basic things. So let me just
mind you, one other thing just before, and just an organizational thing. And since Anirban is also here, Anirban, after Shubhajit, are you willing to give us a spiel on random matrices?
Okay, so this I can try. Yeah, so maybe maybe after he finishes, then I can try and
yeah. So that will mean probably what I mean. So Shubhajit will probably, I mean, December there will probably be several turns missed. So most likely this Shubhajit will go on till mid-January or thereabouts. Is that right, Shubhajit? Shubhajit?
Sorry. It took me some time to unmute myself. Yeah. I think so. Yes, I think because this is also going to be a bit more technical, I think, than flavor. I will plan to go.
So tentatively think mid-January on it one. Is that okay?
Yeah. It's fine with me.
Terrific. Thanks. Yeah, good. So now we have 3 speakers like that.
Great. Okay, very good. Yeah. So, all right. So then, yeah. So I will say a bit about discrete models. So we'll not do full convergence of anything. It will be too difficult. Firstly, I am not the right person to do it anyway. But so let me indicate. So let me give in a way generally what is going to be the type of thing that general framework, so to speak. So general setup, let's say, is going to be like this. So there will be some discrete models. What is a discrete model? So there is some lattice. Okay, so we have a lattice like Z2 or triangular lattice. Okay, so some lattice will be there in the plane, and then we define discrete models in a domain. Okay, so the general setup will be like this. So there will be some domain. So omega is, you can think of omega as a simply connected region. Okay, some simply connected region along with 2 marked boundary points, A and B. So they could actually be prime ends. So you could take even omega to be a slit domain and A and B could be the other sides, so to speak. So all that is okay. Anyway, don't worry about all that. So what we do is we discretize this. So you fill it with a fine lattice with a scaled picture of your lattice. So lattice, let us call L. So this is a copy of delta L. So where the spacing has become delta. And then so we define a model, so there will be a probability distribution, and these things also will get approximated by some points. So A and B will not necessarily lie on the lattice. So you take some points which are close to that, A delta and B delta. Okay, and by omega delta, I will mean basically delta L intersected with omega. So you take your lattice and intersect it. Okay, delta should be sufficiently small. Sometimes a little bit of care is required. Some models may require you to be a little careful. Otherwise, it may not. There may be some problems. But generally speaking, it's okay. So you think of A delta as a point close to A, B delta is close to B, and omega delta is the lattice restricted to scaled lattice restricted to omega. And now what we have is a discrete model.
Sorry, Manju.
Hello.
So I think so. Essentially, so because when you take the delta mesh, it can potentially, for example, if there is a bottleneck, it can potentially get disconnected. So I think we take probably the connected component of some point or something. Or
yeah. So yeah, I am kind of ignoring that. Also, in some models, you have to be a little careful to take care of parity stuff. And I think if you take dimer model and things like that, there may be some other issues also. Yeah, I am ignoring that. Like Shubhajit says, so we take. I mean, so it is it's some connected sub.
But if you take delta fine enough, small enough, won't you get connected?
Yeah, eventually, yeah, but you have to be
not necessarily, right? I mean, you could have, say, thinner and thinner and thinner and thinner.
Thinner and thinner. Okay, for unbounded regions, or even bounded, yeah.
I think
if thinner and thinner.
If you have a slit domain, you might have problems. I mean,
yeah, right.
Yeah. But it is some approximating ones, and then you define some random paths. So gamma delta, let's say, is a random lattice path. Omega delta from A delta to B delta. Okay, so we will call mu delta the distribution of gamma delta. So what kind of random paths I'll come, but in general, it will be, the setup will be like this. And the question is whether when, so the question that one asks is for this. So as delta goes down to 0, as mu delta converge to some mu, a probability measure on continuous. So by the way, random path, I mean, let's assume all these are simple paths. Okay, random simple path. So all the models we will look at, they will be random lattice, a simple lattice path, something it may do this. Okay. Not something like, I mean, okay, you can also consider things like random walk, which intersects itself, but let's, for the, in the context here, let's assume they are simple. So as delta goes to 0, does, so this is one question, will you get a mu? So that this mu is, of course, then mu should depend on, upright it can depend on many things, mu omega AB. And I mean, so if I think that this mu depends on mu omega AB, I mean, also there is a question of maybe not depend on lattice also. Usually we expect that to not happen. Whether you approximate it with triangular lattice or square lattice, it shouldn't matter. But let's anyway, this mu omega AB is some measure, let's say whether such a thing exists. And then for various reasons, there is this conformal invariance conjecture. I cannot explain this much. So whether the conformal invariance conjecture is that these measures have a conformal invariance. That is, if I have omega to some omega dash, I have a conformal bijection. and A goes to A dash and B goes to B dash. In many situations, we understand that this conformal maps extend all the way to the boundary, and phi of A will be well defined as a single point on the boundary. It's true if it's Jordan domains, for example. So phi of B is phi of B dash, is B dash. So conformal invariance is the statement that if I take mu on omega dash A dash B dash, that is same as the measure on omega AB pushed forward by the conformal map phi. So this is equality of two very different things. One is on omega you fill the lattice and then take limits. That's how you get the measure mu omega AB. Mu omega dash A dash B dash is defined by filling omega dash with a fine lattice. Then the claim is that in the limit, there is this thing that if I take this continuous random trajectory in omega, this is my continuous random trajectory, and map it by phi, then here is omega dash and maybe A dash is here and B dash is here. So this gamma is the random path distributed according to mu omega AB. So this gamma dash is phi of gamma. So that will give a path from A dash to B dash in omega dash. So the claim, the conformal invariance question is whether this is true, that gamma dash has the same distribution as the gamma I would get by filling this with a lattice. Okay. So it's a lot of symmetry. It's a big symmetry question. So that is a big question, and it is expected to hold. The reason I am writing it is all these are only questions. Of course, whether this is, if such a thing exists, this mu is called a scaling limit of these mu deltas. Scaling because we are scaling down the lattice. Okay, it's delta times L. Okay. And then conformal invariance is something about the properties of these limits, and it is sometimes expected to be true. So I will give examples. So where it's expected to be true, some proved, mostly unproved, very few models where it is proved. But it is recognized to be a very powerful symmetry. If it works, then we can say a lot about the limit, not merely that scaling limit exists, but we can say a lot more. So another thing, which is what Shram brought in, so is the domain Markov property. This is going to be there in many situations. Domain Markov property. So let gamma be distributed according to mu delta. Mu delta in a particular this, right? Mu delta in omega delta, A delta, B delta. Okay, so let's say gamma is my path. Well, okay, the delta is not so important. Gamma is a path in this discrete lattice, okay, which is distributed according to this. Let's write gamma as it has some, it starts at gamma 0, which is A delta, goes on up to, the length is not fixed necessarily. So it will have some number of steps which may depend on n gamma. What I meant to write was n gamma. So the length of the number of steps will itself depend on the path, and that last point will be B delta, right? So the statement is that conditional on the initial part, let's say gamma naught, gamma 1 up to gamma k. So that means you know the path up to a certain point. Okay, let's say this part we have conditioned on. What remains? Conditional on this, the future path, which is, let's call it gamma k plus 1 up to gamma sub n gamma. So this one is, what is it? It is a path. It is a path joining, this is gamma k. It is a path joining gamma k to B delta, but it is, so since I originally assumed all my paths are simple, it also is constrained to stay within, not only within omega delta, but it's also not supposed to hit the already existing part, gamma 0 up to gamma k, right? So this one has the same distribution as mu delta in this is a question. So this is a path in omega delta, but subtracting the initial segment, gamma naught up to gamma k. So let's say we remove that in our domain, and then, the A delta, now the initial point becomes gamma k. And the endpoint remains the same. So, yeah, so this future is always a path here. Domain Markov property is that that's exactly the same kind of random path that we would have in the reduced domain, meaning it is the mu delta measure on this reduced domain. That is the domain Markov property. Okay, it may be true, it may not be true. So the point is there are many models which have the domain Markov property. So the way we will have is, so now I will introduce some models, only a few. So it is easily checked in many models. Whereas this one is conjectured in many models. It is usually not, it is not at all something that is, it's never trivial. It is largely unknown, conjectured in many models. So this also is a sort of conjecture only. I mean, in many models, it is conjecture. Showing scaling limit, I don't know if there are many situations where we know scaling limit exists, but we don't know conformal invariance. Maybe these go hand in hand. I'm not sure. Shubhajit might know better on this.
I mean, essentially the proof involves knowing the conjecture limit, essentially. So
yeah. So to go, at least in the cases where this works, it's unlikely one will do this without doing this. It seems to be the case. And very few are there for which it is done. But there are. But assuming all this, but if all this were true, if the answer is yes to all three questions.
I mean, so for example, if the limit is, in many discrete models, if the limit is SLE, then actually conformal invariance follows basically by conformal invariance of SLE. So.
Right. So yeah, so suppose, right. So yeah, you're right. So exactly. So if true, but yeah, no, you're right. So yeah, so the point I was about to say the point that Shubhajit just now mentioned. So the point of all this is, if yes to all three, if all three questions are yes, then this mu should have conformal invariance plus domain Markov property. So this mu is on continuous paths. So this is the limit.
So just one question. In the known examples, what are some other examples? So what are some such examples of mu other than SLE?
No, I mean, I am about to say that if yes to all three, then this has to be SLE.
I see.
Because of this, because if you believe that all these three are, if this is something at the discrete level, we will usually have it. The reason domain Markov property is easy to have is that we will have it at the discrete level itself. And then it will go through to the limit, should be usually okay. The conformal invariance, usually the question is what is it at the discrete level which will lead to, there is no conformal invariance at discrete level ever, but what is, there may be some hints of it or some approximate version of it, that is the difficult part. But if the answer to all these three is yes, then the limit measure will have both conformal invariance and domain Markov property. And we saw that implies that this mu is the SLE kappa measure for some. Okay, so I should say one thing, because I never defined SLE kappa measure on other domains. What I mean by this is that it is by this we mean The
Manju,
image,
can you just one more time repeat why you are saying that the limiting measure is the SLE kappa measure? I mean, I think...
this one, so this was the, so I remember Shubhajit remarked at that point, when I was doing this, so where is it? So the lonar evolution is defined with any driving function, and then we put square root kappa times Brownian motion. What I mentioned was that the square root kappa times Brownian motion has two properties, the Markov property and the time space scaling property, which is equivalent on the lonar side to these hulls having the scale invariance property, and they having the domain. This is the, I called it conformal Markov. If you want, you call it domain Markov.
Okay, fine.
So that's why this, so whatever it is, it has to be this SLE is the idea.
Great, thanks.
So, but since I never defined what is SLE image, SLE kappa in other domains, it's just, it's the image of SLE kappa in upper half plane. We only defined SLE kappa in upper half plane 0 infinity by a conformal map.
So were such scaling limits Schramm's original motivation for defining or introducing SLE?
Yes, exactly. So this was his motivation. In particular, there were a couple of models which were particularly motivating.
Low-period random walk, I think, right? I think the first model that was,
so the one he was able to do was this. I will introduce 3 models. So we will introduce, we mentioned 3 models now. This is all in abstract. So one is called loop-based random walk, and then there is critical percolation interface.
Second one is Smirnov, no? Or
I mean, proved by, but I think it was already in Schramm's original paper. He had the idea, and he also knew that it would be SLE6 and all that. He didn't have a way to prove means conjecturally he knew that it would be SLE6, meaning, but he did not have a way to prove the conformal invariance and hence also the scaling limit. So that he didn't have. But in the original paper of Schramm, it is already mentioned. He thinks it is SLE6, etc.
Yeah. So how did he come up with this 6?
So that is the type of thing I hope to do a little bit of calculation today.
Terrific, thanks.
So maybe to see where, assuming all this also, which kappa, I mean, okay, in some sense it should be, you have to find some property of the discrete paths, something you should be able to do, and see the corresponding thing in the continuous among all the SLE kappas, which one has that property. So that is the way you usually try to find the kappa. It's not necessarily easy or something, but at least usually it's easy to heuristically figure out which one it should be. Showing the existence of limit and all are very difficult. But if you have an actual model, which you can do some calculations on, you should be able to figure out which SLE kappa it should converge to. I mean, just conjecturally, for some calculations. Because on SLE kappa side, we can often do many calculations. It is amenable to calculations, and that's why it works. So these are the 3 models. So as you said, so this was in fact Schramm's original motivation for introducing SLE. In particular, he had these 2 in mind very much. And soon after, at least I don't know if self-forwarding walk is mentioned in the original paper, but soon after they also talked a lot about self-forwarding walk. Today we know conjecturally what it should be. So let me not make a suspense of it. This will converge to SLE2. This will converge to SLE6. This will converge to SLE 8/3. There are many other discrete random models which are some are known, some are not known. All these Ising model, Potts models, many things are there. So I myself don't know too much about them, so I will not talk about them. So some, as Shubhajit said, he may talk about some others like this harmonic explorer. That's another discrete model that was introduced. So one of the things that in the beginning at that time people were okay, they found a few and they wanted, although many were difficult and it was recognized to be difficult, they wanted to have some some discrete paths for every SLE, for every kappa. And I think that's how the Harmonic Explorer business came, right? I mean, if I'm not mistaken, it's
I don't know. So Harmonic Explorer is also a kind of like a preparatory paper for this GFF level lines, I think, which is basically kind of the precedent of the, that is actually one of the tools that they developed, is used heavily in their.
So, but this Harmonic Explorer, is there a parameter in it, or does it go to SLE4?
I think SLE4.
But they also introduced, I think, a one parameter family of discrete random models, which converges to SLE kappa for every kappa. I mean, that's also there, I think.
Yeah. So that you can do. I think in this, I think at GFF level lines, you can get.
There you have to do, you run gradient lines instead of level lines. You do some gradient lines. They will go to different SLEs, I believe.
But by the way, just for a small trivia, like. Okay, so all these small that Manju is talking about are really coming from statistical physics. But there was another very interesting case that was made possible by this discovery SLE. So Mandelbrot, I think in late 70s, he was when he was discovering this Mandelbrot space and all these kind of things. By just doing a simulation, he conjectured that if you look at the outer boundary of which is called the Brownian frontier. So if you take a two-dimensional Brownian motion and you take its outer boundary, make sense of it some way, its Hausdorff dimension is some weird figure like 8/3 or something, whatever.
4/3.
So 4/3, right? Yeah. So for example, so then actually they proved, I think Lollerstrom and Werner proved that the outer boundary of Brownian frontier is a SLE curve, and that's one of the very dazzling, I think, very intriguing consequence or spin-off of this SLE thing.
Yes. It's so I was thinking whether or not to mention this. So this is another thing. It's not only for discrete random models. Some existing problems about Brownian motion were actually solved by introducing SLE. So the one that Shubhajit mentioned is that you take two-dimensional Brownian motion, run it up to time, say time 1 for simplicity. So it will look something like this. You look at the outer boundary. So you take the complement of the path and take the outer boundary. So the Hausdorff dimension of that was conjectured to be 4/3. So it's not an isolated problem. There are many other related problems. For example, there were other types of problems about Brownian motion. For example, you start 3 Brownian motions, planar Brownian motions. Let's say you start them inside the unit disk at 3 different points. And then you ask what's the probability that up to time t, they don't intersect. I mean, Brownian motions will not hit each other. What I mean is the entire paths remain disjoint like this. So this was expected to behave like t to the minus some power. Okay. So what power is the what power? So for 3 there is some number, for 4 there will be another number, and so on. All these exponents, so these are called intersection exponents for Brownian motion. All these were determined, and this 4/3 is part of that story in some way. But it is all these were solved using these were all solved using SLE, and this is not much to do with the discrete models, but it is a very funny thing. Since you mentioned it already, let me say that why. I mean, once Shyam gave a lecture, I still remember that, in 2005. So then he was trying to explain why it was possible to do this kind of, we know so much about Brownian motion. Why was it possible to do this kind of problem after SLE, but not without SLE? The thing is, the outer boundary is a highly non-parameterized curve. I mean, it is coming. So every time Brownian motion comes, the outer boundary is coming from a lot of contributions from many different visits of the Brownian motion. So it's not from one. So it's not, there's no direct handle on it. This is what he said. Whereas what happened with this SLE is that this outer boundary is same as SLE 8/3, okay, locally. And for that, we remember that the Hausdorff, this is the leading to what Shubhajit is talking about. We said that when kappa is between is less than 8, the dimension of the SLE kappa is 1 plus 2 over kappa. If you put 8 by 3 here, you get 1 plus 3 by, sorry, something is wrong here. Is it 1 plus 2 over kappa? Sorry, 1 plus kappa over
8.
Kappa 8.
1 plus kappa over 8. So that becomes, in this case, 1 plus 1 by 3, which is 4 by 3. That's how. So the outer boundary of Brownian motion is very much the same as SLE 8 by 3. Okay. So one can make it very precise. So that is how this 4 by 3 comes. So these are other things for which SLE was useful. Okay. So now let me go to these models and maybe describe. So first, let me talk about critical percolation. So this was the one where conformal invariance, etc., were actually stated and so on. I don't know if in case of, it was also done for loop-based ANOVA, but originally it was done for this. So there is, let me insert a, so what is critical percolation? Let me insert a picture. So I just downloaded one picture from which will be. Okay, I don't know how big this will be. Okay, it's a reasonable size. So this is a domain. So think of this as a domain. In the lattice here is the triangular lattice. What I have drawn is, I mean, this I have not drawn. I just downloaded from internet. This is hexagons. If you think of the centers of the hexagons, they form a triangular lattice. Each hexagon is adjacent to 6 other hexagons. So instead of drawing the vertices and edges of the centers, we are here the hexagons are shown. So what is percolation here? So this is a big subject. I mean, I am least qualified to talk about it much. So what we do here is very simple. So each face is colored blue or red. Here there are 2 colors. Actually, this is a bad choice of picture. Actually, there was a better picture, I think. Okay, so because I'll now have to ask you to imagine different colors. Now I see that it's completely wrong, not what I wanted actually. So the boundary, sorry, it's completely wrong. So let me use different colors. So let's say there are 2 colors, blue and red, but this one, unfortunately, you have to imagine this to be blue. I mean this. So imagine this to be blue and this to be red. I took this. Actually, maybe it is okay, but is it? Sorry. No. It is fine. Actually, I don't need to do all that. Maybe it is okay. So let's see. Okay. So what you do is, okay, forget the colors. Okay, sorry. So each hexagon is colored. Red or blue with probability half. Okay. So each one will be red or blue with probability half. Then by just some planar topological duality, so it turns out that, so I have drawn these edges, this blue to this edge. So either there exists a blue left-right crossing. What I mean by that is there is a sequence of blue hexagons which connect the left to the right. Okay, so what I mean is, suppose this is blue. So if you have these things, let's say all these so 2 adjacent means they share an edge. So this side is blue. So if I have a bunch of blue things like this, oh sorry, 1 second. Yeah, so if you have a bunch of blue ones like this, then you have connected the left to the right. Okay, but in that case you cannot also connect the red from top to bottom. This blue will block, or this is an exclusive, or there exists a red top down crossing. Okay? So exactly one of the two will happen. Either if the blue doesn't exist, then the red will connect from top to bottom. This is just some planar duality. I mean, it's kind of easy to imagine. I mean, well, more or less easy to see, but this is a fact. So percolation is about the study of connectivity. Okay, percolation is about the study of connectivity. So for example, so you can ask, so in very general terms, one can ask, so for example, you take like we did earlier, so let's take omega, and with instead of 2 boundary points, let's say you have A, B, C, D. So, and you do everything with delta. That is, you fill it with a delta lattice, which is either Z2 or hexagonal lattice and so on. And you ask what's the probability that in percolation path, so we fill this with hexagon, let's say we fill this with hexagons, and then each is colored blue or this. So I ask for the probability that there is a blue, so let's say we have colored this side blue, this side blue. So what is the probability that there is a crossing from this arc to this arc? Okay. So so one of the things, so what physicists, okay, there were 2 levels at which conformal invariance was there. So physicists said a lot of things about critical percolation being conformally invariant. What it meant is a little unclear. I mean, so they did many calculations, but what exactly is the scaling limit of critical percolation is a very complicated thing. So this critical percolation is, I mean, percolation is the coloring of hexagons by blue or red. What do we mean by scaling limit of such an object? I mean, where you make the mesh size smaller and smaller. What is the limiting object even? What is, to talk about limits, you have to put these things in a common space and take a limit. So it's actually quite difficult to talk about the limit. What is the scaling limit of percolation? What does it mean? It's, for example, not the naive thing where you have a coloring of each point in the plane. Such a thing is useless probabilistically. You can't answer any questions of interest there. So you can't have a question coloring of every point in the plane by blue or red independently. That sort of an object is useless probabilistically. So it is too big an object to talk about. So some people try to, some people like Langlands and so there is a paper by Langlands and some others, so Pulio and Santova. Where they try to make many of these conjectures very precise. So one of the ways they did was to say that, okay, you consider something like this, fill a region with delta lattice. They were thinking of Z2, but okay, it doesn't matter. Let's say this way, as delta goes to 0, this should converge to something, okay? It should converge to something that depends on omega and this A, B, C, D, okay? But this also should be conformally invariant. Should be, it's a function of, there's only one conformally invariant quantity for a region with 4 marked boundary points. Namely, it is what is called the extremal distance of AB to CD. Okay, so if you don't know what extremal distance, don't worry. I mean, I'll not define it now, but there is one conformally invariant quantity here, and it should be a function of that. And there was a prediction, in fact, due to Cardy, what this function is. So it is in the original form, it's a little complicated to say, but there is a simple form observed by Carlson, which is like this. So the Cardy prediction. So if you take an equilateral triangle. So
Manju, just one thing. So this extremal distance, it's the same thing as you uniformize it to be a rectangle and then look at the breadth, right?
Exactly. So yeah, you said it. So this one, you just take it to map it to a rectangle, so that this is phi of A, phi of B, phi of C, phi of D, and you make this length 1. Usually they make it pi, I think. And then this length is not in our hands. That length is the extremal distance.
So no, so I think my confusion is, so what does this have to do with percolation?
No, it is, no, it doesn't have to do with, I mean, okay, so it has to do with if it, no, the conformal invariance conjecture says that if this limit should exist and should be conformally invariant.
I see.
So then there is only one option. It has to be some function of this extremal. It has to be a function of this cell.
I see. Okay, great.
No other choice. Actually, this is only one aspect of conformal invariance. There can be many more complicated questions one can ask, but this is the simplest one you can say of a crossing event whose limit we expect to be conformally, I mean, invariant. Then it has to be a function of that. And I'm saying what is this has to do with, but any this, yeah, I will come to this point. So.
But hang on, one more thing. So the crossing events, even forget the, I mean, you don't need to go to the scaling limit to get the crossing event, right? I mean, so this is.
Yeah, but in the finite level, it is something, whatever, it is some complicated thing which depends on delta and everything. We don't know what, there's no exact solution to that problem.
Cool. Plus it's a random object, right? So you want at the end, I mean, because
no, we are looking at the probability only. Yeah, this is actually this probability. This if you fill omega with a fine lattice and look at the crossing probability.
Yeah.
So we are looking at the probabilities only.
Oh, I see. Okay, great.
So this probability
I was wondering what expectation is being taken. Okay, good. That's the one. Okay, great. Thanks. Yeah.
This is percolation on delta L intersection omega. Okay. So with this probability half is important. That is what is critical here. There are more general statements which I'm not going into. So this the fact that this doesn't go to 0 itself, or go to this probability doesn't go to 0 or 1 was known. This is called the Russo-Seymour-Wiertz theorem. But it is not, but then you expect the limit to exist. And the conformal invariance allowed Cardy to make exact prediction in the following form, that you can always conformally map it to this situation, ABCD, where this is an equilateral triangle. Okay. So if you ask for the crossing event here. So in other words, you are looking at the limit in this particular setting. This is exactly X. Okay. So if you were to write it on rectangle, it would involve the conformal map from triangle to rectangle, which can be done. It's some hypergeometric function, but it is easy to state it for equilateral triangle that this is how it is. If you have an equilateral triangle and you break it into this one side into X and 1 minus X, the probability of crossing this side to that side is exactly X in the limit. This is the Cardy prediction. But this is where I just wanted to make one remark that yes, so this was a precise type of conjectures that Langlands and others did. But I think it was one of Schramm's brilliant points that so there's the full percolation scaling limit which physicists are talking about. Then there is the limit of this probabilities alone. So Schramm took this intermediate thing of paths. Okay, and that was possible, and that made a lot more because that's more than just a crossing, let's say. It's finer information than finding limits of probabilities. It is less fine than finding the full scaling limit, whatever that thing is. But at the level of simple probabilities, any function of extremal distance is conformally invariant. You can't get characterization. But by going into this intermediate level, which is neither just individual crossing probabilities nor the full scaling limit, but at the level of distribution of random paths, Schramm was able to get this characterization of what are the possible limits as SLE kappa. So you now know what the putative limit should be. So how do you get a path here? This doesn't look like this. In this, there is no path. What is the path? So this was the way Schramm introduced paths into this model, where it is not obvious that there is a random path. So let us say you want a path from, now let's do it a bit differently. Let's say you want a path from, let's say this is A and this is B for simplicity. Okay, you could take the opposite side, it doesn't matter. But imagine this whole thing is red. Okay, you imagine this side is also colored red. That's important for what I'm going to say now. So the way Schramm got a path in the percolation one was to what he introduced as exploration process. So his idea was this: you start at A, you enter here. The rule is this: keep red to the left, blue to the right. Okay, so you enter here. So see the color of this. It's either blue or red. Suppose it is blue. Then always the rule is keep blue to the left, blue to the right and red to the left. Okay, so you go like this. And you have now come to the new one. So suppose this one, you look at the color of that. Suppose that is red. Then the rule says you keep that to the left. You come like this. And then now you have to know the color of this. If it is blue, you will go like this. If it was red, you would go like this. So like this, you keep moving. Always blue is to the left and red is to the, blue is to the right and red is to the left. Okay, so you will never get stuck actually. So if you see, now you come to this situation, you have to know the color of this one. So it's either blue or red. If it is blue, you will turn the other way. And so whether you will turn right or left depends on whether that new one you hit is blue or red. And there is no problem at the boundaries because when you hit this side, red is to the left. So you will keep going till you hit a blue one, then you will come up. Or if you hit this side, you will keep blue to the right and keep moving on the boundary till you hit a red and then you come up. So this path can only do one thing. It has to exit. It's all a finite thing. So there is only one place it can exit, namely here. So whatever it does, it will give you a random path from A to B. This is how a discrete random path. So this is called the exploration process. So you have introduced an exploration. So now this is the discrete random path we are talking about. So the claim is that this discrete exploration paths. So if you take omega AB and then make A delta, B delta, and then define this discrete gamma delta, the discrete exploration paths. The claim is that the theorem is the claim is gamma delta converges in distribution to SLE 6. Okay, so this is not known except in a limited sense. Known. Okay, this is known if we use hexagonal lattice.
And you're going to say a bit about the 6 at some point? Or
yeah, the 6, where does the 6 come from? Okay, so you have to figure some property. I thought, okay, shall I say that or shall I?
Whenever. It's not urgent that you say it now.
Okay, so then I will introduce the other model. So this is a model where paths are not obvious on the face of it. I think it was Shram who introduced these exploration paths and so tease out random paths, and probabilists have for long studied random paths and limits. So that's a framework we understand. We understand what it means to take weak convergence and weak limits of random paths and stuff like that. So this all fell into, but full percolation scaling limit is much more complicated, what it means and so on. So in the other two models, the paths are already there in the very definition. Okay, this one, the path is not so apparent in the definition. In loop-based random walk and self-forwarding walk, there are, so let me just quickly introduce them. The self-forwarding walk, it is still a largely open problem. So here, what you do is, again, you fill. So again, we'll have omega delta and A delta and B delta. This is all a lattice domain. So let's say we have used delta Z2 for simplicity here. You could use other lattice, but let's say we have done that. So you consider, so gamma delta is a random path, random simple path from A delta to B delta inside omega delta with probability, sampled with probability proportional to, so the usually used word is mu. It conflicts with my measure notation, but doesn't matter. So let me just use mu to the minus number of steps, length of gamma delta. So this is the number of steps in. So for each path, you give a weight, which is mu to the 1 over mu to the length of gamma delta, okay, where mu has to be chosen appropriately. The specific number. Okay, so in case of Z2, it depends on the lattice. If it is Z2, then this mu is square root of 2 plus square root 2. So this is, this is a theorem of Smirnov and Hugo-Dimitrov. So what you have to choose a mu which is very specific. Why? Why not uniform on all things? So instead of this simple path, suppose you were to look at all paths. Okay. So all lattice paths going from A delta to B delta, that would be like a random walk, right? But if you want to define random walk with 2 fixed endpoints, it's not correct to give uniform distribution. You should give 1 over 4 to the length, because each step you usually random walk, we say you go with probability 1/4 in each direction. So each step costs you 1/4. So longer paths should be penalized accordingly. You should take 1 over 4 to the number of paths. Then you get actual random walk. That is what should be called random walk from A delta to B delta inside omega delta. So this is the exact analog, but instead of 4, it is a number mu. The 4 comes because the 4 comes there because in Z2, if you look at on Z2, number of paths of length n is 4 to the power n. Each time you can take one of 4 steps. But if you do the same for number of self-forwarding walks, so that is simple paths, then that goes like mu to the n, where mu is a specific constant, this 2 plus root 2. So one can show there is a particular mu with which that goes. So that's the one that you should use here. So that's called the self-forwarding walk measure. Okay. So this is the gamma delta, and it is conjectured to converge to, so this is fully open. So that was known when the previous one was known when you use hex lattice, but here it is conjectured that this gamma delta converges to SLE 8/3. Now again, it's in the same type of question Mahan asked, why 6, why 8/3? That I will come to a little bit. Okay, so this is one other model which is largely open. This is almost completely open, fully open. So this was a big thing that Smirnov and Hugo-Dimitrov did, but it didn't lead to this one. So they, anyway, so that's another matter. So then long before this self-forwarding walk problem has been open for a very long time, now maybe 70 years or so. But so at some point, Lawler had introduced, so this was first introduced by some chemists. So Lawler had introduced an easier version. So this is an easier version of self-forwarding walks. Okay. So this one we understand much more. Okay. So let me describe what this is. So it's an easier version of, so again, let's take some lattice, omega delta, A delta, B delta. So you can imagine that we have filled it with delta Z2 or some other lattice. Again, you look at all lattice paths, simple lattice paths. So gamma delta, a simple lattice path in omega delta from A delta to B delta. Okay, but how is it defined? So the way it is defined is it's different from both self-forwarding walk and normal random walk. So let me describe it. There are multiple ways to describe it. Let me choose a way which makes it actually, although it is probably would not consider it the simplest way to describe. This is actually I like this way slightly more. Okay, whatever. Okay, so what it is that how is it defined? Okay, So conditional on, so like a random walk we are going to do. Suppose I am given up to k steps. Suppose I know this is gamma 0 is a delta, then gamma 1, and so on up to gamma k. I have developed the path up to a point. What is gamma k plus 1? It is going to be one of the neighbors. Okay, in this case, the way I have drawn the picture, there are 3 possible neighbors. If it is Z2, okay. So there are 3 possible neighbors. So what are the probabilities with which you will go to them? If it was normal random walk, you would also include the backward path and you would go with probability 1/4 to each of them. Okay. So gamma k is this tip. So what are the probabilities? So I will write this probability. It is, okay, so let me just, so it is the, let me write H, let me write hk of, so if it is, let's say u is this one, okay, so u is this, what's the probability I'm going to u rather than the other ones? It is hk of u b delta over what is hk? Hk of uv is the probability that if you start a random walk at u, okay, simple random walk started at u, so if you, that is simple walk, random walk started at u, hits v on or before exiting this omega delta minus all the things that already exist. So what you do is you calculate from here the probability that a random walk will exit through b delta. So hk of u b delta is probability that a random walk started here will hit b delta before hitting any other point on the boundary or the path of already that exists. Okay. So you go with probability proportional to that, but if you add these 3, you will get that this is actually, okay, so this is not this, it's, okay, first actually, let me write this with probability proportional to this. So you go with probability proportional to this. If you have higher probability, if you come this side, maybe you have less chance to avoid this. So this will have lower probability and so on. But it's actually with, we can write down exactly the normalization here. With probability exactly, we can write it as hk of u b delta by whatever I had written, hk of gamma k b delta times, this is dk of gamma k. So what is dk of gamma k? The degree of gamma k in here, meaning in this case it is 3. Okay, so this is the normalization. So this is one way of
4 o'clock.
So this is one way of describing this loop arranged random walk, that you go with this probabilities proportional to your. So how do you define, for example, hk of uv? So how is it defined? I mean, so this one you can just, if you want to understand what this hk of uv is. So let me describe it for hk of ub delta. What is hk of ub delta? You take the value 1 here at b delta and put 0 everywhere on the boundary. Also on this one. Okay, so you find a harmonic function is the, you find a phi of u where phi is a discrete harmonic function that is 1 at b delta, 0 on boundary of omega delta, union with all these gamma 0 up to gamma k also. There also you put 0. And then you find the value of the harmonic function at u. That is your hk of ub delta. Is this okay? I mean, It's a little complicated looking definition. You're taking steps with probability to make it simple. So this used to be called Laplacian walk also, I think. So anyway, so is there any question about the description here?
Yeah, I mean, can you just, so say that one more time.
Okay, so
in the just the electric case, So
yeah,
you're taking a random walk. Right?
Yes. No, this one. So it is. So you can write it without reference to random walk. Having developed the step up to this point, you have to decide which of the three you will take. Okay. Sometimes it may be only two. Sometimes it may be only two or only one also. So it depends on how it looks so far. So, for example, if it is like this, then it is not allowed to go here, not allowed to go here. It has only two possible steps that it can take, either this or this. So we have to tell what are the probabilities with which it takes. Now, this is not a Markov thing in the sense, the usual Markov thing depends only on where you are. But this depends on the entire path. It depends on the entire path. To figure out with what probability I should go here and what probability I should go here, I solve two discrete harmonic functions. One discrete, but
it's still domain Markov, right?
Yeah. So this is kind of apparent from the way it is being defined. So to find hk of u by delta, so let's say this is u and this is v. So you take a harmonic function, discrete harmonic function, meaning it satisfies mean value property at each vertex, which is 1 at this point and 0 on this part, old part, and also on the boundary elsewhere. That gives you one harmonic function.
I see. Oh, I see. So, okay. So the thing would be basically you put a Dirac on, say, the boundary of hyperbolic space and extend it inward.
It's really the Poisson kernel, right? I mean,
that's what it is. Okay, great, terrific. Okay. Yeah, I was trying to wrap my head around it.
Sorry. I mean, I should have uttered that word first. I think this is the discrete Poisson kernel in the reduced domain with this at the pole or whatever at this B delta, right? So. But you have to find that for u and for v, you have to find both of those, and then the normalization is given by this because this is a harmonic function. Poisson kernel is a harmonic function. If you add it on the neighbors, you will get the degree times the value at this point. So that's why it is hk of gamma k. So this is how the normalization is. So probabilists have a different way of describing it. So that's actually simple, but it's not simple. Well, okay, it's simple to describe. So probabilist way of describing it would be, you run a random walk from A delta to B delta. Every time you form a loop, you erase the loop. Okay, sorry, this is a problem.
So sorry, Manju, when you say that you run a random walk from to B, means you take the condition measure that it starts at A delta, never leaves the domain in between, and
yes. So firstly, so we have to take, you're right, actually. So that is also something I have to do. But let's imagine that we know how to run a random walk from A delta to B delta. It is a, so you just run a random walk from A delta to B delta, which stays in omega delta, let's say. And then you chronologically erase the loops. Okay, so you get a chronologically means the first loop that was formed should be erased first. So it will, in this case, let me indicate, it will go like this. The first loop, this formed a loop, I will erase that, and then it goes like this. But then this has gone here and come back here and jumped here. So next I will go like this. But then, this will erase a loop. So it will go up to here and then maybe it goes up to here and something. Whatever, in the end you get some simple path. So that is actually same as this. So that is another way to describe the loop erased random. So the statement is, but the reason why I describe like this is, you see, unlike the other two models, you already see things. If you believe discrete Poisson kernel converges to continuous Poisson kernel and various things, you already have some conformal invariance and those type of objects built into the model itself. The Poisson kernel is already there. In self-forwarding work, we have nothing.
Except that, I mean, see, the thing is so there has to be some statement made about running a random walk between points of the disk, boundary of the disk, and some conformal invariance of that process. This other point, how are these two pairs of points? I mean, the beginning point and the end point, how are they varying? What is the law?
No, they are fixed. They are fixed. To be fixed. these we fix and we just define a random. So we have to, if you remember, my abstract construction is that for every disk omega AB, I discretize and I define a measure of paths going from A delta to B delta.
Right. Okay.
So this is my definition of my measure. This is how I define a random path from A delta to B delta by this construction.
Yeah, no, I get that. So by conformal, you probably, okay, so at the end of the day, what will conformal invariance mean? It basically means what conformal maps of, say, the disk. Think of this guy as a disk.
Yeah.
Conformal maps of the disk which keep these 2 points fixed.
No, you map it to any other domain. So you can do this in any omega. So like here, so you do it in omega by discretizing this with Z2. You do it in omega dash by discretizing with this with Z2. So we have a definition of a gamma from A delta to B delta, assuming it has a limit that is some gamma. It's a random measure on paths from A to B staying in omega. Similarly, we have a limit here, which is a measure on paths from A to B in omega dash. The claim is that if you, this random path, if you map it conformally, it will have the same distribution as this random path.
Yeah, so I guess the point is, I mean, okay, so what
just to answer to Mark, I think when you're talking about this taking, I think, so basically what you take, you conformal map with 2 marked boundary points.
Exactly. So that's
right. So here, sorry, I meant here that this A dash is phi of.
So here is the thing. So what that probably means is that you can always normalize your domain after, I mean, post facto. Once you've got conformal invariance,
yes,
you can assume that you're running this thing in a round disk, going from, say, either 0 to infinity, or either from the south pole to the north pole, or from the left end point to the right end point of the diameter.
Yes. So at least for simply connected regions, so it's only, there is only one definition one has to make, and that's going to be our SLE. We did it upper half plane 0 infinity.
Okay, great. Oh, I see.
Yeah.
Nice. Very nice.
Plus,
plus it should be invariant under this one parameter family of conformal automorphisms which stretch it. I mean, so basically Z goes to lambda Z, where lambda is any positive real.
That's part of the assumed conformal invariance. For SLEs, it is a checkable fact. I mean, we check. That's why we can define when so the point you are making is important. When I defined what is SLE from, when I said SLE in omega from A to B is the conformal image of SLE from in upper half plane from 0 to infinity. That is only well defined if it is already invariant under scalings, which it is.
Thanks.
Right. And all these, so this is the definition of loop-based random walk. But my point is that it's already defined in terms of harmonic functions and other things, which make it less surprising that you should have conformal invariance in the limit. So loop-based random walk converges as delta goes to 0 to the claim here is SLE with parameter 2. Okay, so those are the 3 models. So I have not now in the remaining time, I want to just say very quickly how this 6, 8 by 3 and 2, can we see them in by what? I mean, so something has to be computed about the discrete model and on the SLE side and matched up to see these numbers. What I'm going to say, if I get time, about SLE2 will be actually, in fact, that is more or less the way the proof is done also. Okay. But maybe I just go to that. But before that, any questions or anything here? So to find which SLE, so if we have in distribution and gamma is expected to be SLE kappa, we need some computation. How to figure which kappa? So maybe for the purpose of saving a bit time, let me very quickly tell what is the special property in these 2 other models and then come to SLE2, where I am hoping to explain. Okay, I have prepared, but whether I'll get time, I'll see. Okay, so what is the special property of
Manju, here is the thing. In any case, next week, Subhajit is not coming on. So you are welcome to take
people
the
are already tired. No.
people are not tired at all. You are welcome to overflow.
Yeah,
I mean, unless you are tired.
No, I mean,
then
well,
in that case, you are welcome to sort of, because this is one of the questions that Balarka had asked long back. I mean, in fact, he had asked me, do you have any understanding of what the hell this kappa means? I said no, and I would like to know.
Okay. Well, I don't think you'll get. So yeah. See, let me pretend everyone else is tired, but mainly I exhausted all I know pretty much. So yeah, there's nothing I have to say. So let me try to finish today. I mean, pretty much there is not really much I have to say, but what Shubhajit is going to say is a sort of continuation, so it's fine actually. So the thing about critical percolation, okay, so maybe in the picture was there. So maybe I go back here and show you. So in the critical percolation, I described the percolation process. So what is the special property of this discrete model, which which will make it? Okay, so maybe I just draw, just let me insert another picture. Try to do the same. Okay, where did it go? Oh, it went somewhere else. Oh, okay. So let me. Sorry. Okay, it has come somewhere, but okay. So for a moment, so you remember how the exploration path was defined, right? So we come from this side. So what I need to do to develop this exploration path is I need to know whether this is blue or red. So let us say this is blue. So let me already, yeah, okay, maybe this is blue. And let's put a few blue here just to save myself time. So how will it go? It will keep blue to the right and red to the left. It goes like this. Then red is to the left, blue is to the right. Now red is to the left, blue is to the right. So it comes like this. Now again, blue is to the right and red is to the left. Now again, it has to go like this and so on. Okay. So where is it going to? That is the question. Okay, so we know that ultimately it will exit here if I put all red here. If you remember, I had asked you to imagine all this to be red also. This thing is not blue but red. But when do you really need to worry about that? So what is the difference between the exploration path going to this point and let's say exploration path going to a different point? Okay, so maybe here is, I'll draw a schematic picture. What I mean is I start at A. There are two possible targets, B and C. Okay, so consider exploration path going towards B. In exploration path going towards B, what you are going to do is this whole side will be blue up to here, and this whole side will be red. Okay, the blue will be this part on the boundary, and it will be. Whereas on when you're running exploration path from A to C, this side will be blue. This whole A to C will be blue, and this side will be red, and you will run it and it will exit here, right? But when will you know the difference? The two exploration paths will proceed exactly the same way till you hit a point in this boundary. Till that point, you don't know whether you are going towards B or towards C. It's the same, right? Because you never had to look at this. The only difference between these two boundary conditions is here, which is blue here, whereas red here. Right? So this exploration path won't feel the difference till it hits this point. So this is the property of this critical percolation path. Gamma delta does not know whether it is going to B or C till it hits the arc BC. Okay, so this part of the arc. Is this point clear? I mean, till that point, is this okay? I mean, till you see the difference in the boundary conditions, how will you, I mean, what difference does it make? You are only doing your decisions based on the colors of these hexagons. You will keep proceeding. Only when you hit the boundary, this part of the boundary, will it make a difference? Is this okay?
Yes.
So this is called locality property, meaning it is locally evolving. It doesn't really know where the target is, so to speak, till a moment of decision arises. Because at this point, if it's red, then it will have to go this, I mean, one way, otherwise it has to go another way. Okay, so when it hits, so that's the difference. So the question is, which SLE has this property? Okay, so it turns out kappa equals 6 alone. So let me just say a word about how that comes. So the what you look at is, I mean, so more precisely, what this translates to is this locality property translates to the following. So you consider SLE kappa. So this is gamma, which is SLE kappa. So you take it starting from 0 going to infinity, and let's take some hull. Okay, some set like this. This is some set A. Okay, and we map it by GA. GA is the map that kills this. GA is the map that kills this. So it's a normalized map. So this gamma will become something else. So this gamma will become gamma tilde, which is GA composed gamma. Or maybe I call it phi. Phi A. So this map, we call it phi sub A, and that is phi sub A composed gamma. Okay, and A is killed by this. All these are normalized at infinity in the usual way. Now, so gamma T is here, gamma tilde T is here. So we can look at the curve gamma tilde T. Okay, so whether, so for example, gamma is actually by GT, it is, GT is a map which kills this part, and then A goes to something. And what do we know? This satisfies the Lohner equation. GT dot of Z is 2 over GT of Z minus UT. Okay, where UT is square root kappa times Brownian motion. So this gamma T will go to some point square root kappa WT. Now let's look at what if you try to do Lohner to this gamma tilde. Okay, so basically locality translates to the following, that gamma tilde also develops like SLE kappa. So what I said here, the discrete locality, if you transfer it, it's a little, maybe it's not that evident right away, but this is, one translates it to this, that this gamma tilde also should develop like SLE kappa. Okay, so that's what it is. Except that it's not parameterized by half plane capacity, but that's a small matter. So that's what locality translates to. In other words, if you look at the maps G tilde T, which kill gamma tilde 0 T, that will map it to some U tilde T, which is GT tilde of gamma tilde T. Okay. So this one, okay, so the fact is, if you also now, so let me translate. So let's also introduce the map here. This is usually denoted H sub T. Okay, so you can first kill A and then gamma tilde 0 to T, or you can first kill gamma 0 to T by GT and then kill the image of GTA. Okay, so this is nothing but phi sub GTA. That's what it is. So if you write down, it turns out, So let me just copy it from here. So this du tilde t, if you look at the stochastic differential equation satisfied by that, like I was doing last time, it turns out to be ht dash of ut times dut. So ut is this square root kappa wt plus kappa over 2 minus 3 into ht double dash of ut dt. Okay, so this is a derivation which I am not showing, but this can be done. Ito's formula and stuff like that, we will get this. The point is, again, like before, if u tilde has to be, for u tilde to be like Brownian motion, so this is dut is like square root kappa dwt. To be a martingale, we need kappa equal to 6. This is how kappa equal to 6 comes. It's not, I don't know if you call it explanation or calculation, but this is the conformal image of SLE is not SLE. I mean, it's not SLE, but it is in only for SLE 6. The precise statement is SLE 6 up to the time it hits A. If it hits A after that, you can't apply. Up to the time it hits A, its image under phi A is also SLE 6.
So maybe the thing would be that, no, does this not give you a necessary condition of sorts that, look, if it is
if and only if, in fact.
Yeah, so I mean, one side, I mean, from the function, isn't one side of that implication that it has to be 6 if it is SLE or something like that?
Yeah, so if it is, then u tilde basically has to be a time change of Brownian motion. The problem with u tilde is that it's not exactly Brownian motion, because this g tilde is, this gamma tilde is not parameterized by half plane capacity. So we don't expect u tilde to be exactly come out as square root kappa wt. So we have this extra term which is actually leads to a time change. This ht dash of wut is what leads to. Otherwise, it would be like developing. Otherwise, this is, if when this vanishes, it would be Brownian motion with scaled by square root kappa. But that time change is involved, which we would expect anyway. Yeah, so this is, you can say it's time change of Brownian scaled Brownian motion if and only if kappa equal to 6. That's
great. Thanks. Okay. Yeah.
So with a drift, it will be something else. Yeah. So this is the way SLE 6 comes out. Okay. Another way to do, yet another way to do is if you can check Cardy's formula. I mean, this type of calculation of Cardy's formula you can do for SLE, which I mean, it's similar to the calculations I did last time, so I will not do now. But that is another indication that it should be 6. But this is what is the key locality property. Okay. So similarly, self-forwarding work has a different property. It has what is called restriction property. Okay, so what that is that if I have self-forwarding work from A delta to B delta, and I cut out some part of the domain. Okay, so this whole thing is omega delta, and this thing is, let's say, omega delta dash is reduced domain. So the distribution gamma delta, conditional on gamma delta is contained in the reduced domain, has the same distribution as gamma delta on omega dash delta. What I mean is self-forwarding walk from A delta to B delta in this bigger domain, if you condition that it doesn't hit this part, it is exactly the same as self-forwarding walk in the reduced domain run from A delta to B delta. So this is the restriction property. Okay. It's not true in general. I mean, you have some random path, you condition it to stay inside, it is something completely different. Actually, its distribution changes. So the question then becomes, which SLE has this property?
This is definitely false for percolation.
So I could not hear it. Your voice was very low.
Oh, sorry. Can you hear me now?
Yes.
Yeah, this is definitely false for percolation, let's say, right? This restriction property.
Yes, you're right. Yeah, it is false. It is in fact false for pretty much anything you think of.
Yeah.
Loop arrest random walk also it's going to be false. Yeah, so it turns out only SLE 8th. Again, there is a martingale one can write, but so it turns out that in this case, yeah, so it is a bit. Maybe I will not even write the martingale. So there is a difference. So it is done by the calculation is you take the same picture here, but you look at HT dash of UT. So DHT dash of UT, there is a, again by Ito formula, one can write blah, blah, blah. Okay, so one is that there is a Brownian term, HT of UT, DUT, that is there. But the drift term has many things. HT double dash of UT squared. I'm just copying from a piece of paper I have here. But just to show you, there is some kappa over 2 minus 4 by 3 times HT triple dash of UT dt. So okay, so there is this. So because of that, so you see you have to, this vanishes when kappa is kappa is 8/3. That is how this comes. Of course, you may object that still it's not a martingale because this term is not 0. There is still a dt term. Okay, so this vanishes, that's correct. And this one is not going to be a martingale, but you have to raise it to a certain power. If kappa equal to 8/3, then this is not martingale because it will still have this dt term. But if you raise it to a power, you can get rid of that. This becomes a martingale. Or local martingale, whatever. So if you raise it to the appropriate power, like I did last time, if you remember, I raised things to a power to get a martingale. XT was not a martingale, but a power was martingale. So this is what you need to do. This 5/8 will do it. And that is how it leads to SLE 8/3. Okay, so yeah, so I have only 2 minutes. So, I mean, so let me just mention SLE2. I was thinking of doing it, but maybe we'll just skip it entirely. So SLE2 is the easier one, actually. Maybe somebody can do a full lecture on it sometime, actually. So yeah, so what do you say, Mohan? So skip that, or I can mention what is it that comes out as martingale, but
yeah, so I mean 2 minutes for what?
To finish. Right?
No, I mean,
so it's already 4:30. So
yes, no, it's okay. If you want to overflow a few minutes, I think people will be willing to listen. So
yeah, I mean, it's already been long. So okay, so let me just say what happens with the loop arrest random walk. See, I had to struggle quite a bit to understand it. I had never read this, so this one I had to. I mean, impressionistically I followed, but then there were some things which I got confused with. So, but it's better to postpone also because there is also a recent paper I saw in preparing for this. This was done by Lawler, Schramm and Werner long ago in 2004 or so, actually, one of the earliest ones. And this is one where everything is known. So self-forwarding work is entirely conjectural. In the critical percolation case, we know it when you use the hexagonal lattice. But in this one, we know it even very fully that anytime you have some lattices going final or even some random walks converging to Brownian motion, then the corresponding loop arrest random walk will converge to SLE2. This type of things are known. There's also some recent paper of Dima Chelcock and somebody, maybe Shubhajit knows. There's a new proof of this. I don't know how it comes. So they mentioned some outline that Makarov and Smirnov had given 10 years ago, and they say that we try to carry out this program for this one, and they give another proof for the not just loop arrest random walk, they have some massive loop arrest random walks and stuff like that. So I don't know much about that. So it's a case where much is known. So let me tell you what is the martingale first of all. Yeah, so what happens here? So yeah, what is it that happens? So let me just check the, yeah, what is the martingale? Where is it? Right. Yeah, so the thing is, okay, so here is one thing. So on SLE side, so we can consider, so fix some Z in the upper half plane and consider one over GT of Z minus this square root kappa WT imaginary part. So let's call this XT indexed by Z. Okay, so this is the XT. Then turns out that XT is a martingale. Again, we can write dxt equal to blah, blah, blah. dxt turns out to be what all? I mean, so in this case, yeah, I just did this calculation, but I have lost it somewhere here. Where did it go? dxt turns out to be, I can write it like this, imaginary part of, so let's remove the imaginary, yeah, so imaginary part. So there is square root kappa dwt over gt of z minus the square root kappa wt square. Again, Ito's formula, we can do this calculation, plus 2 minus kappa dt over gt of z minus square root kappa wt. Here there is a cube, I think. Yeah. Okay, so you get something like this by Ito's formula. Again, this is a martingale when kappa is 2. If and only if kappa is 2. Okay, so that's how this is going to arise. But what is the relevance of this martingale to the loop erased random walk? So the thing is, yeah, I will just give impressionistically. So let's say what is imaginary part of GT of Z. So we have here gamma T, and then if you map it by GT, you get, this is UT, let's call it UT, which is square root kappa WT, which is the image of gamma T, right? So that is what it is. And then, so GT of Z, so Z is some point here, up there. And okay, I should, let me write Z here. And then this is GT of Z. Let's call it W. What is the imaginary part of 1 over W minus U? Okay. So let's say W is in the upper half plane, U is on the real line. What is this? So if W is A plus IB, then this is nothing but W minus U squared. So you get A minus U squared plus B squared. And then in the numerator, you have, what is it? W bar, which is, you will get B minus B or something like that, right? So you see, this is the Poisson kernel. Of upper half plane with a pole at, I mean, the pole or whatever you call it at U evaluated at B. Evaluated at not B, W. So this is the Poisson kernel here. And by the conformal invariance, it is also the Poisson kernel in this at Z with a pole at gamma T. Okay. So, I mean, it's just a conformal map. If you, here, this is the Poisson kernel evaluated at W with where the Poisson kernel is rooted at U. And if you map it this way, this is same as, so the imaginary part, so imaginary part of 1 over GT of Z minus square root kappa WT is the, okay, if you do minus 1 over pi, there is a minus and stuff like that. So this is the Poisson kernel on upper half plane minus gamma 0 to T with I'm calling it pole, sorry if that is the wrong language, at gamma t evaluated at z. Right, because these things, of course, harmonic functions go well with conformal maps and so on. So it is just the Poisson kernel there. Now, how is it related to the random walk? I mean, so if you see, pretty much this is the basic point. Actually, I will just end with this point that is, so what is it in some sense? What is the Poisson kernel evaluated at z and this? So it is, in some sense, if you start in some sense, if you start a Brownian motion here, what's the probability? It will exit this domain h minus gamma zot at this point. In some sense, this Poisson kernel is that probability, right? I mean, I'm speaking loosely here. It's the probability that Brownian motion started from here, exits the domain through this point. This is the harmonic measure, right? So that's what it is given by. Is this okay? Hello?
Yeah.
Okay. So in some sense, that's also, yeah, so that's the probability that this hits, meaning when it hits this, it hits it here for the first time. So one way to run the random walk, loop arranged random walk, let me go back to the pictures I had here. What is the loop arranged random walk? I described how it is developing each step, okay? One equivalent way of doing it. So I described two ways of doing it. I mean, this is a slightly third way if you want. One is I gave this Poisson kernels in terms of which it develops and so on. Another is with this loop arranged random walk. There is a bit of reversibility because of which what one can do is, if you want to figure out the probability with which you will go to particular u, one way of formulating it is you can start a random walk here and run it till it hits this omega minus the part that is already there. And you have to, you consider the probability that that will happen at this point rather than at the other point. Okay, that's actually also the Poisson kernel, if you want, with pole at b delta and evaluated here, right? Something like this. Yeah, sorry, I will not be able to explain too well now. The point I want to say is that this yeah, so you express the corresponding things here. What is done in this paper of Lawler, Schramm, and Werner is they take the discrete, I mean, loop arranged random walk. Well, rather, let's do it in the upper half plane if you prefer. So let's say we have the discrete loop arranged random walk up to some time, and then you have the driving function for that. Okay, so this is gamma delta, and then there is a u delta of t by the Lohner mappings. So g delta t is mapping this and so on. So what the key point to show is u delta converges to square root 2 times Brownian motion. That's not quite, I mean, it depends on what topology you show it under. Those are very technical things that exist actually. So, but the gist of it is that this driving function for the discrete process should be something that is converging to the driving function of what we think is the limit, namely the SLE2, whose driving function is square root 2 times Brownian motion. So you have to show this u delta is converging to Brownian motion. For that, you have to write this, to see how these things evolve, you pretty much have to write this picture in the discrete setting with the discrete Poisson kernels. And by invoking some convergence of discrete Poisson kernel to the continuous one, you can show that this u delta behaves like square root 2 times Brownian motion. Yeah, sorry. I mean, yeah, maybe I will just end with this because I don't think I will be able to explain that very well. The point is that in the discrete time, if you write the evolution, instead of this type of differential equation, you will write a somewhat approximate difference equation. And it will, yeah, so it will fall out of that. I mean, so you get basically what the way in which it comes out is that u delta and u delta square t both will be martingales, approximate martingales. So that's how you show yeah, from the evolution of the loop-based random walk using Poisson kernels, you have to understand the evolution of U delta, and it ends up showing that this happens. It's not too long, but I don't think I'll be able to explain it very clearly. So let me just stop here. Yeah, so that's pretty much all I wanted to say.
So thanks a lot, Manju. Thanks a lot. Thank you. Thank you. Yeah. So anybody, any questions? We've kept on bothering you throughout.
So I can't hear. Hello?
Yeah. Subhajit, you wanted to say something?
No. Yeah. I just wanted to thank. That's all.
No, thanks. Yeah. So, so Shubhajit will continue, because that I also would like to see this Hausdorff dimension computation. I have never actually seen this actually. So that would
Let's see how. Yeah, it will be difficult to match you. You did an amazing thing. Yeah.
So Manju, these final slides also you're going to be sharing, right? Or is it automatically?
That's already, it's automatically.
Yeah.
The recording I will put on the same YouTube channel. I mean, it's a channel. So now the third one is also there. The fourth one I will put sometime. Yeah.
Okay, then I'm ending the meeting unless anybody has anything to say.